Welcome to section 1.5 part B. The last video talked about inverse functions, and the second half of this section starts on page 40. I'll begin with a quick review of logarithms. So you should remember from Algebra 2 that this expression in example 1 is read log base 2 of 32. You need to know how to correctly talk about logarithms because they're weird. And the first thing you need to know is that this number down here is the base. If you see a number, that's the base. If you don't see a number in this spot, we assume the base to be 10. This number right here, 32, is called the argument. And the correct way to read this is log base 2 of 32. Now this is an operation. We are doing log base 2 to 32. 32 is the input, and hopefully what you remember is that the output of this operation corresponds to an exponent. And the way that we figure out what that exponent is by thinking of this logarithm as a question. And log base 2 of 32 is really asking the question, 2 to what power equals 32? And the answer to that question is the answer to the logarithm. In other words, 2 to what power is 32? Well, 2 to the 5th power is 32, so the answer to this logarithm is 5, because that's the correct thing to fill in the question mark in this question. This is how we think about it. But really, if you think about it as a function, 32 is the input and 5 is the output. What you notice right away is that this is the opposite of an exponent. More on that later. In example 2, you'll notice that we have a base of e. Now, in the first question, 2 to what power equals 32 is a question that we could answer really easily. But if we come down here and think about the question for the second logarithm, which would be e to what power equals 4, this is no longer a question that we can just answer in our head. It doesn't mean that it doesn't have an answer. For example, if you grab your calculator, you can find the number e. Here's my calculator. And I will zoom out for you here. So I can find the number e, and e is right here above the natural logarithm. And if I press second e, and you just take it to the first power, we get 2.718. That's what e is. Well, I'm wondering what exponent would I have to put in to make that 4? Well, let me try something. Let me try e to the second power. That turned into a 7, so that's too big, which means there must be some number in between 1 and 2. I'll try it again. How about e raised to the 1.5 power? Oh, that's getting closer. So you can probably imagine that the answer to this question, e to what power equals 4, is going to be a decimal number between 1 and 2. We don't have any good mathematical way to figure out what that number is. We do, however, have a calculator. And so a log base e is actually a natural logarithm. There's a special word for it. And we can use the ln button. And if we take ln of 4, the answer we come out with is 1.386. That's the answer to this question, e to what power equals 4. And I can prove it to you by taking e and raising it to the 1.386 power. I'll stop there even though I'm approximating. And I get basically 4 back out. So coming back here to evaluate this logarithm, the only way we can answer this question, e to what power equals 4, is using a calculator. And the calculator button is ln of 4, and the answer we get is 1.386. And just like above, even though the one above we could do in our head, the answer to a logarithm, the output, is the exponent of a problem with this base. Okay, so we think of the output in both of these as being the exponent. Hopefully that background knowledge works for you. I'll give you a couple quick Edpuzzle questions to double check that you understand this, and then we'll get going with the text. Logarithmic functions. If a is any positive real number other than 1, The base A exponential function is 1 to 1, and it therefore has an inverse. Its inverse is called the base A logarithm function. By definition, the base A logarithm function, y equals log base A of x, is the inverse of the base A exponential function, y equals a to the x. These are inverse functions. Now, in this exponential function, we expect that a is only a positive number, and in fact, it can't equal 1. So that's true for the inverse range as well. The domain of this base A logarithm function is positive numbers not including 0, which is the range of that exponential function. That makes sense. They're inverses, so their range of 1 is the domain of the other. The range of this log base A log base A function is all real numbers, which was the domain of the exponential. Remember, we're actually not talking about a single function here. We're saying you pick any number you want for A, and you will get a function of this type that is related to a function of this type. So what about the graph? Well, because we have no technique for solving for x in terms of y in this exponential equation, there's no algebra thing you can do, well, so far, we don't have an explicit formula for the logarithm as a function of x. However, the graph can be obtained by reflecting the graph of the opposite or inverse function across the line y equals x. That was covered in yesterday's video. Logarithms with base e and base 10 are so important in applications that calculators have special keys for them. They also have their own special notation and names. As you just saw, log base e is the same thing as ln, which is the natural logarithm, and log base 10 is the same thing as just saying log x. We call it the common logarithm function. The graph on the side here shows you the graph of the exponential function in black, and that's 2 to the x. And the inverse is in blue, and this is log base 2 to the x. And they're opposites because they're reflected. That means any input value from this graph is an output of this graph with the corresponding output as its input. Let's talk about properties of logarithms. Because a to the x and log base a to the x are inverses of each other, composing them in either order gives the identity function. This gives us two useful properties. I'll let you read them for yourself. Notice that we are limited by the domains of these functions. Sorry about the noise pollution there. As I was saying, we are limited by the domain in some ways, namely that in the second function down here, we're talking about positive x's, actually in both. And in the first one, a can't equal to 1. That just wouldn't make sense. Let's do a quick check to make sure that these properties make sense to you. On the screen now, you see 4 examples that are going to ask you to apply these properties. You should be able to simplify each of these expressions using these properties. Take a moment to think about which property applies, and my hint to you is that you shouldn't be using a calculator. This shouldn't be difficult. Once you see which property applies, the answer should jump straight out at you. All right, easy enough. This is an application of the very first property, and the answer is just 12. Notice that the bases are the same. If the logarithm here is saying 4 to what power equals 12, if you take the answer to that logarithm and make it an exponent, 4 to that exponent is going to be 12. Same logic, different format right here. The bases are the same. This is kind of the opposite application. Now, here you're going to have to recognize that e is the same thing as the base of ln, and the answer is just 3. And in this case, if we do 2 to the power of log base 2 of x, the answer is just x. They are opposite functions. Whatever you plug in on the inside comes all the way out when you compose the two. Moving on. These properties help us with the solution of equations that contain logarithms and exponential functions. In example 4, which I'll model for you, we're going to use the inverse properties. Here's what solving A would look like. My goal in this equation is to get x by itself. Don't get thrown off by the t. The t is just some extra information. Now, I know that this side of the equation equals that one. So the first step is the only one that you have to think about. And what I'm going to do is something called exponentiating. That is, I'm going to make each side of this equation into an exponent of a very particular base. And that base that I'm going to use is e. Now, if these two sides of the equations are really equal to each other, then if I take e to the ln of x, it should equal e to the 3t plus 5, because we said that these two are the same. So e to that exponent should equal e to that exponent. Now, the reason this was helpful to me is because e to the ln of x equals x. E to the power of something is the opposite function as ln of something. Those two functions essentially eliminate each other the same way addition and subtraction eliminate each other. So x comes down by itself. Now, there's no such luck on the other side. So on the other side, this is what I have left with, but actually doesn't really matter because I've solved for x, and that's all I was supposed to do, so I can leave my answer just like that. For b, we'll use the opposite property. In other words, I'm given an equation that's in the exponential form. I'm going to do the same thing to both sides in order to try and get x by itself. And what I'm going to do to both sides is I'm going to apply the natural logarithm. If these two sides of the equations really equal each other, then taking the natural logarithm of one side has to equal, sorry about the parentheses here, it has to equal the natural logarithm of the other side. That's just the first rule of algebra. Now, the reason this is helpful is because ln is the opposite of e. If I didn't have a base e here, I wouldn't be using ln, I would be using a log with a different base. But since I do have an e, those two cancel each other out, and 2x comes down next to the natural logarithm of 10. To get x by itself, I divide by 2, nothing could be easier. We get the natural logarithm of 10 divided by 2. As far as I'm concerned on a quiz, that's a fine answer. But if you're taking the AP exam and it's a calculator section and you need to get a decimal answer, you would go to your calculator, take the ln of 10, which turns out to be 2.302, and you would divide it by 2, getting an answer of 1.151. This is what it looks like in the book's terms. You'll see that they did the same work that I did. And we'll move on to log properties. The logarithm function has a number of useful arithmetic properties. You should remember these from Algebra 2 or review them if you don't. Basically, there are rules about how you can rearrange logarithms. I'm going to ask you a couple of leading questions in Edpuzzle, but I'm not going to stop to explain them in particular detail. One note is just to pay attention to where the exponents are in each of these properties. The properties should go in your notes. Moving on. Okay. Your book next has an interesting exploration activity, which could be fun if you have the time to play around with your graphing calculator, but I'm not going to spend time on it in the video. Moving on very briefly to the change of base formula, which is the last property. Again, this is a property that you should recognize from Algebra 2 and be able to apply, but I'm not going to explain examples with it right now. Graphing, however, is pretty important. So remember that the graph of a logarithm is essentially a reflection of the graph of an exponent, and that means one thing that's really important. It means it has a vertical asymptote. And the vertical asymptote is usually at 0. It doesn't have to be at 0. We could move the function around by changing something next to the x in parentheses, subtracting or adding. One way that the book has you think about graphing is in terms of the change of base formula. I don't know if this will be very helpful to you, but if you think about it, they're saying the graph of ln of x you should memorize, and then think about all other logarithms as basically that same shape divided by a constant. So basically it's looking a little smaller or a little steeper. Applications are pretty important. In the last section, we used graphical methods to solve exponential growth and decay problems. We can do the same thing for properties of logarithms. Let's start with some simple setting up interest problems. You should remember the compound interest formula from the last video and be able to apply it. I'll give you a second to try and solve this one on your own before I show you the actual work. Here's the final answer.